right? So I'm not going to really go in detail to the theory, but essentially, right, what kind of NMR is you apply like a magnetic field to any molecule, really, right? It doesn't even have to be organic molecules. And essentially, remember, electrons have two properties in terms of they have like electronic properties and magnetic properties, right? So what it does is when you're subjected to a magnetic field, it causes you to spin in a certain direction, right? And that's kind of what the up and down, if you ever seen in an orbital, it refers to the different spin, right? So then they get aligned and they spin a certain way, right? And then when you kind of hit them with RF, I guess it would be radiation, right? Just at the radio frequency, right? Usually somewhere in the 100 megahertz to up to 1 gigahertz range, right? They're going to basically create signals, right? And then it's kind of, what is it? There's usually an internal standard, which is like TMSCL, right? I mean, modern day spectrometers, you don't really need to put that in, but it's more of that we define as 0, and then everything based off that is shifted a certain value, right? And based off the shift, right, the multiplicity, right, and the integration, we could basically determine the exact structure. Maybe if I have some time, I'll show you guys like one of my NMR spectras, and we can analyze and go over what I have there. So anyways, in terms of how to practice them, right, for both BISCO and boson, right, generally what they'll ask is either they'll give you a molecule and expect you to draw a spectra, but most of the time, usually they'll give you a spectra. They'll give you a chemical formula, right, or molecular formula, right? And then they basically want you to determine the structure out of that, right? So there's a couple of things you really need to understand, right? And the main two things is the location, the integration, and the multiplicity, right? But before we can get started, we have to get kind of familiar with the idea of what's called chemical equivalence, right? So I usually like starting off with this problem, 15.1. This is from your main textbook, right? And basically, chemically equivalent protons, right? They will show up at the same location, right? Because you can't really differentiate between those, right? And what that basically means is if you were to like replace a proton with like, I don't know, tritium or deuterium, right? Do you still have the same compound, right? So that replacement test is a good way of identifying whether things are chemically equivalent, right? So there are actually two types of chemical equivalence. So one is called homotopic, right, which is they are completely equivalent in terms of that if you do a replacement test, right, you will get the same exact compound. Then you have another sort of chemically equivalent protons called enantiotopic, right, which means that if you did a replacement test, you get a pair of enantiomers, right? But remember, can we separate enantiomers through any sort of, physical methods that like you guys might have learned in Royale lab? Or do they have any different physical properties, right? No, right? That's the answer is no. The only thing that's different in enantiomers is the way they rotate plane polarized light, right? That's when you guys probably learned, I think, in chapter 5, right? If you use a polarimeter, then if you have an excess of one enantiomer over the other, right, it's going to rotate that light in a different way. But chemically, right, they're equivalent, and there's not really any way to physically separate them except for like something called chiral GC or HPLC, right? But those are just, analytical methods that labs use, really kind of beyond what you guys need to know right now. And then the last type is diastereotopic. So let me actually write this write this down before we. So those in bosons class probably already learned these terms, right? So I will write chem equivalent, right? Replacement test produces what? The same compound, a pair of enantiomers. Same compound, right? Replacement test makes same compound. Okay. Then we have enantiotopic, right? Kind of the name tells you it's the same thing. It's chemically equivalent, right? But the replacement test, right, makes a pair of enantiomers. Oops. I'm just gonna write this over here. And then the last type is diastereotopic, right? And these are chemically unequivalent, right? Because when you do a replacement test, you're going to get a pair of diastereomers. And as we've learned, diastereomers are compounds that have different physical properties, right? So just a quick kind of recall of Orgo 1, right? Diastereomers and enantiomers are both types of stereoisomers. Diastereomers, right, have different, chemical and physical properties, right? Enantiomers, all they do is they rotate light a different way, and that, also really where it comes down to is the direction is different, right? There's no like chemical difference, but when you if you learn about like pharmacology and really when drugs interact with your body, right, then having kind of an enantio pure substance can be, very useful because the way it interacts with the, I don't know, I guess your enzymes or whatever proteins or I don't remember biochem too much, but basically at the position it interacts with your body, it wants to interact in a certain way. You guys probably learned about phthalimide, I believe, where it was one enantiomer caused birth defects and a lot of side effects for pregnant women, and the other one cured something, right? So that's why enantiopurity is very important, especially in pharmaceuticals and medicine, right? Because the way your body interacts with one enantiomer over the other can affect kind of effects that drug has in your body. So that was just a quick recap of that. So these are chemically unequivalent, right? Good Lord, my spelling is off this morning, afternoon now. Chemically unequivalent, and what do we say? Replacement test produces a pair of diastereomers. Okay, so maybe let's go down here. Actually, I'll put that in the middle. That'll be, whoa. Let's open that. Okay, so I'll start with 15.1 now. And then basically ask you for each of the following compounds, determine whether the two protons are shown in red are homotopic, enantiotopic, or diastereotopic. Okay, so we start with A. So we have OMe here. We have our pi bonds, right? And our two protons in red are these ones, right? So one way to always kind of surefire check this, right, is just to do a replacement test. So let's call this H1, we'll call this H2. So if we replace H1 with D, like for deuterium or something, right? We'll say this is D1, right? And the other one was just H, so I'm not even going to show that. And then if we replaced H2, let's say another deuterium, we'll call that D2. So we have D2 here, right? So you guys tell me, are those the same compounds? Are they diastereomers, right? Think about rotations, axes of symmetry, right? If you want to quickly determine that kind of stuff. You could try rotating it this way, see what you get, or rotating this way. So Isabella says they're the same. Got any other takers? Shiz this says they're enantiomers, right? Okay. Any other answers? Okay, so obviously it's a little easier with the technology here. Right now, if I just did a simple flip or essentially a rotation along an axis of symmetry, right? So one thing to make clear, right? You could say that there's an axis of symmetry, right? If I wrote this OME group like this, it would make kind of even more sense. Oops. Right, but you're allowed to basically cut through a group in half, right? This OME in this case, oops, where's the white? Right, so like, doesn't matter what group is, if it's the OH or whatever, you could cut like an axis of symmetry through here, right? And there will be an axis of symmetry, right? And in the case of benzene rings, right, you could also kind of, just consider that. Like, it doesn't matter the position of the pi bonds, right? Because they're all always resonating with each other, right? So now, if I were to take part of the molecule, let's do a rotation. So we'll do a horizontal flip, right? And what do we have here? Obviously, this kind of moved over, but it's fine. It's still OME, right? We have D1 here, right? Like I said, it doesn't matter, right? So, or is it maybe easier to see now, right? Are they the same? Yeah. So also Shizda, right? A quickly way to determine whether they're enantiomers or not is there any chiral centers, right? And by definition, right, at a sp2 hybridized carbon like this, right, or this, you can't have a chiral center, right? Because remember, you need 4 distinct groups, right? You can only have chiral centers at sp3 hybridized carbons, right? So in this case, you couldn't even have a chiral center, right? Because it was attached directly to a benzene ring, right? So that's always a quick way to, make sure you don't mess up whether it's homotopic or enantiotopic. So in this case, if they produce the same compound, right? Are these homotopic, enantiotopic, or diastereotopic? Homotopic, right? So we could just label this homotopic. Okay, let's do another one. Let's actually do B. That's a good one. So B, I will write it out, and then actually I'll draw out both structures, and then you guys can kind of easily see. So we have a Cl here, right? So the protons of interest are, we'll call this H1, and we'll call this H2, right? So now if we replaced each of them, okay, this was, we replaced D1, the other one's still in the back there, right? And then if we replaced the other one, right, I'm missing something, Cl, right? So obviously what's not shown, but I guess to make it a little clearer, right, is there's the H in the back here, and here it's that, right? Or maybe for sake of consistency, I'll draw it the same way. So here we had H, and this would be the other one is now replaced with the deuterium. Let's call them both D, so not to confuse. It's not different deuteriums, right? So what is, are those the same? Are they diastereomers? Are they enantiomers? So Isabella says enantiomers. Sorry. Okay, so no other takers, but yeah, they're enantiomers, right? Lena agrees as well, right? So if we look at them, right, all that's different, right? First, there's no other. First thing you should always look for, right, in the case where when we did the replacement test, right, the first thing we did is notice that because now this is a D, this is an H, there's one carbon going this way that's connected to a chlorine and one carbon going another way, right? There are 4 distinct groups. So we created a chiral center after the displacement test, right? This is a chiral center. Same thing after this replacement test. We created a chiral center, right? So now a quick way to always tell whether things are enantiotopic versus diastereotopic is if there are any other chiral centers on the molecule, right? Then remember, essentially what's the difference here is there's a D on a wedge and a D on a dash, right? So if we put these kind of up against each other on like a mirror plane, so let's say we drew it this way. So this would be kind of the wedge facing this way. That would be the dash. This was our D, right? And then against the mirror plane, right? So, or was there CL here? Oh, oops. This is our D, this is our H, this is our H, right? So if we were, this is basically this drawn the other way, right? Because you see the CL is pointing this way, right? The D is pointing towards the other D. So essentially they are non-superimposable mirror images of each other, right? Or a quick way to also determine that they're enantiomers of each other, right, is that the only group that's different here is the D, and the D was on a wedge on one structure and it was on now on a dash on the other structure, right? So by definition, they have to be enantiomers, right? And the only time you'll get diastereomers, right, is if you see other multiple stereocenters, right? So if we had another stereocenter, right, like let's say, I don't know, we had a stereocenter, say this was Cl, and we were basically analyzing 2 hydrogens here, right? H and H, right? Now, when we do a replacement test, we get different chiral centers here, but the chiral center, let's say here, remained the same, right? Now, let's say this was, one, after doing one replacement test, you get RS, the other replacement test, you get SS, right? Those are a pair of diastereomers, right? So basically, you could always determine whether things are enantiotopic or diastereotopic is when you do a replacement test. And if you get a pair of enantiomers, right, it's basically there's no other chiral centers present. That's the only way you can have an enantiomer, right? But if you have other chiral centers present, then those protons are diastereotopic, right? So in this case, since they are just enantiomers of each other, they're enantiotopic. Actually, let me write it here. So enantiotopic, right? So let's do another problem where we might run into kind of more enantiotopic. So make sure I write it right. Let's see which one here. Oh, C is actually perfect, right? So we did C, which is kind of almost similar, right? Now I'm not going to draw the other structures, right? You're going to have to be able to do this quick enough to determine equivalence on your exams, right? So, right, do a replacement test on these hydrogens here. So let me actually make those red for y'all. So call this H1, H2, right? Check to see if there's any other chiral centers, right? If there are any other chiral centers, right, then you're not forming enantiomers, you're forming diastereomers, right? So you guys can take a minute, and then after a minute, you guys can post your answers in the chat. Okay, so what did everyone get? Homotopic, enantiotopic, diastereotopic. Okay, Serblina says they're diastereotopic because there are 2 chiral centers. Do we agree with her? Any other answers? Diastereotopic. Okay, so looks like we're all kind of getting this, right? So if we did a replacement test, like here, if we made this D, right? So let's say, actually, we could quickly do the chiral center here. So this is 1, this would be 2, this would be 3. So 1, 2, 3. This is going that way. So that is R here, right? So that chiral center will always remain the same, right? So let's say if we replaced like D on the wedge here, right? Now I guess you could quickly do it enough, but technically these carbons would take priority 1. So let's just say when D's on a wedge, it's an S. That would mean when D's on a dash, it would be R. So you'd have an SR and an RR, right? And remember, to be enantiomers, all chiral centers have to be the opposite configuration, right? So that's why as soon as you see a molecule with multiple or 1 or more other chiral centers besides those protons you're looking at, right? Those protons have to be diastereotopic because you're always, when you do a replacement test, you'll always get a pair of diastereomers, right? So they're chemically unequivalent, right? So here they're diastereotopic, right? Because we get a pair of enantiomers. Since the other chiral center, you don't do a replacement test on it, so it'll always be unaffected, right? So generally, whenever you see multiple chiral centers, the protons in like CH2 groups, so this is a good thing to remember, usually CH2 groups, right? If that molecule has multiple chiral centers, right, those CH2 groups are not going to be enantiotopic. They're going to be diastereotopic chiral centers. Just kind of a quick, pattern recognition you can remember. So multiple chiral centers, diastereotopic. If you don't have any other chiral centers, right, then they'll all be enantiotopic, right? So kind of important. So there's one other, I don't think the book mentions it, but I like kind of bringing it up, is in terms of across an alkene, right? So let's say we had let's use white. Let's say we had a molecule that looked like this, right? And we are essentially trying to analyze this proton H here. So this is the other kind of case where you could get diastereotopic stuff. So you had H1 and H2, right? So actually, it would be better if it was like this. Right, so an alkenes, you basically have to check if you create like something that's like cis trans or something like that. So in this case, right, we could say, or easy, right? So we could say on one side of the alkene, the biggest group is always going to be this ethyl, right? So these 2 protons here, H1 and H2, right? If we were to do a displacement test, right, as it is right now, right, we can't really give any sort of, what is it? This is a terminal alkene, right? So it doesn't have any sort of stereoisomerism, right? But would these protons, if you did a replacement test on it, does it create the same compound, right? So if I had D on the top, so basically if I had, let's go orange for one root, right? So if we had D this way, this is still H, this is the methyl, and then the other way, let's say it's blue, right? D would be here, H would be here, and this is your methyl, right? Are those the same compound, or are they a pair of diastereomers? Like, are they different? For a group that don't attach 4 parts to a center tab, the H atoms don't count as the same. So you mean like a methyl group? basically, right? Because you have 3 hydrogens here, or I'm not sure. Maybe if you can give me an example later. Yeah. But anyways, these orange and blue structures, right? Actually, a good way to determine if they're the same compound is what is the stereochemistry of the alkene that's orange? Is it what is it Z or cis, right? Or is it E or trans? Whichever notation you want to use here. So remember, the biggest group on one side, right? So the orange one, right, is going to be Z, right? Or cis, because remember, the biggest group, so the way to always do stereochemistry for alkenes, right, is cut it in half and look at groups on each side across the alkene. So here it's ethyl, and here D is bigger than H, right? It's a deuterium, right? So they are cis to each other. So you could say this is cis or zusamine. So that's same, right? Right here, it's going to be ethyl here and D here. Those are trans or enantiomer, I think it's called, right? E to each other. E for, I always remember E and Z is E for enemies. Enemies want to be away from each other. And Z is kind of like same, right? I don't know. The E for enemies is how I always remember it, right? So if this is now a cis alkene and this is a trans alkene, right? Are those diastereomers? Remember stereochemistry for alkenes, right? We don't have chiral centers here. You can't make enantiomers, so are they diastereomers if they're cis versus trans? Okay, there we go. Yes, right? Remember, a cis alkene versus a trans alkene, they have different chemical properties, right? Cis is going to be higher in energy, right? And it's going to, have a different boiling point or something because the groups are close to each, the largest groups are close to each other. That creates steric repulsion and torsional strain across the alkene, right? When you have something trans, the groups are farther apart, so there's less repulsion and less strain on the alkene, right? So they are diastereomers, right? So if they are diastereomers, what is the relationship between H1 and H2? Are they diastereotopic, enantiotopic, or homotopic? So this is the only part, for some reason, maybe Klein, I just never saw, for some reason, he doesn't cover diastereotopic protons in alkenes. And in case you do get an alkene group, right, I just want you to be able to, determine if you have chemically unequivalent protons on one side of it, right? So it's not only in the cases with chiral centers, right? It's also across alkenes because there is stereochemistry there, right? So those should cover all the cases, right? So let's move on to kind of quickly determining, right? So as I mentioned early on, and what some of you might have already learned is that chemically equivalent protons, do they produce the same signal or different signals? Same signal, right? So the next exercise we're going to kind of do is if I give you a molecule, can you determine how many different signals are at each? And this is usually for those who are having boson, he asks a question like this, but he kind of goes a little bit extra where he'll ask you to determine every different signal and the multiplicity at that location, right? We'll probably, when we get to multiplicity, I'll try to do a question like that. But this will help for people in BISCO too, because all this exercises together help you just analyze the spectra and going forwards and backwards, right? Oops. So we have OME, right? And this is, we're going to do B. And then we have a methyl group. So this is, I don't know if toluene takes the priority. This is anisole. This is paramethyl anisole, maybe. I don't remember the naming. Oh, it's going to be para for sure. It's just, I forget if anisole takes priority or toluene takes priority. or it's either paramethoxytoluene or paramethyl anisole. Doesn't matter for names, whatever. Okay, so let's determine the different number of signals we accept, right? So one thing I always like is mapping out all my hydrogens, right? So 3 H's here, right? Say H here, H here, H here, here, then H. Okay, so starting at the methyl, that's connected to the oxygen here, all 3 hydrogens here, right? Are they going to produce the same signal? Or so basically, what I'm asking is first to check if they're, homotopic, enantiotopic, diastereotopic, and if they are either homotopic or enantiotopic, right? They are going to produce one signal altogether, right? So here, do they produce one signal or multiple signals or what? One signal, right? Because if we did a replacement test on all of these, you can't differentiate. So another quick kind of thing to always remember is CH3 groups, right? Within each other, right? So there might be multiple CH3 groups on a molecule, right? And if that entire molecule has symmetry, then certain CH3 groups might be equivalent to each other, but within a CH3 group, right? So within a CH3 group, all 3 H's are homotopic, right? Which just translate to chemically equivalent, right? So it's quick. Whenever you see those methyl groups at the end, they're always just going to produce one signal. But, something like, let's say an isopropyl group and the rest of the structure here, right? All 6 of the protons here will be chemically equivalent because you can't differentiate between both methyl groups now either, right? So just the thing to remember is think about symmetry as well in the whole molecule, right? But within a CH3 group, they're always equivalent, right? We'll get to examples with groups like that. Okay, so we'll say this produces one signal. What color should I use? Just use orange, right? So one signal here, right? Okay, let's move down to the other methyl group, right? Based off that logic, we get one signal, 2, 3, also one signal, right? One signal there. Okay, so now the aromatics are a bit tricky, right? But still, let's think about it, right? Let's label these A, B, C, and D, right? Now, are any of these chemically equivalent to the other? Right, so think about axes of symmetry, right, and doing a quick replacement test, right? Or are they all the same, right? Maybe that's a viable option too. Okay, so Isabella says A and B are equivalent, C and D are equivalent, right? But is A equivalent to C? No. Okay, does everyone agree with that? What Isabella said, right? So this is like when you're dealing with, especially with aromatics, right? Think about always like location in terms of where they are, right? So there's an axis of symmetry cutting down this way, and then there's an axis of symmetry technically cutting down this way, right? Because this is a methyl group and this is a O methyl group, right? So A and B, right? They're different than C and D because they are closer to that O methyl group, right? So in terms of location, you can't distinguish between each other, but you can distinguish between A and C and B and D, right? Because C and D both, they're closer to the methyl group, right? So if I did a replacement test, like if I put D here and D here, they would be different compounds, right? But if I put D across, to B, right, versus A versus B, you couldn't tell the difference, right? But if I put D on, the D here, right, then you can tell the difference. So C and D are equivalent, right, because they're both on the same side of one axis. right? And then A and B are equivalent, right? So just look at any other groups that are present, right? Those closer to one group over the other, right? So with aromatic rings, you just got to be a little careful to make sure, right? You know if all of them are the same or different, right? And it has to do with the substitution, right? So here we get, let's say one signal from these two and one signal for these two. So a total of 4 signals from this molecule, right? And kind of a quick example of what I meant by the symmetry in aromatics was if I did something like just do regular O-methyl, or yeah, just for the sake of it. So you get one signal, right? We can automatically say one signal here, right? But here's the same thing. There's no group here, right? But I'm gonna tell you that the protons here and here are equivalent, right? The protons here and here are equivalent, right? And then here, right? So the orange, right? If you did a replacement test on each of those, right, you'd get the same thing. But if you compared them to a blue position, it would be the same thing, right? It would be 2 away from the O-methyl group. So essentially you can distinguish between the orange and blue locations. And then the red location is extremely unique because it's para to the O-methyl group, right? So here you would also get 4 signals, right? So let's do, if you are confused a bit with the, aromatic ones, there's a couple of more in this one that does aromatics. Let's do a linear one though. Just to kind of, I'll give you guys some time to work on this one. Let's do J. Actually, let's do I and J. Right, so that's I. Give some space, and we'll do J down here. I don't know why I put a dash over there. So diastereotopics, right? Remember, they're chemically unequivalent. So each diastereotopic proton produces a different signal, right? So that was the whole thing in terms of homotopic and antiotopic and diastereotopic, right? Homotopic protons, right? They produce the same signal. Same with enantiotopic. They just produce enantiomers, but the signal's the same. Diastereotopic ones, right? They are, you could chemically differentiate between them. So those always produce unique signals, right? So let's do this. Okay, so yeah, take a few minutes to do those. Okay, so for I, how many total signals did we get? So one person sent me 6. Any other takers? Or did anyone else get 6 as well too? Okay, so let's go over them. So first, all the protons here, right? They're all the same, right? They're part of a methyl group, right? They are homotopic. They produce one signal here, right? Maybe let's use a different color. So make this easy to follow. We'll use orange, right? Here is another methyl group, right? Is that equivalent to the other methyl group that's on the left? Just look at location quickly, right? No. So this is a distinct signal as well. So they're not identical methyl groups, right? Now the kind of issue is the two CH2 groups in the middles, right? So if we draw this one and this one, if we did a replacement test on them, right? Do we get a pair of enantiomers or diastereomers if I did this? And then if I put a D on the other one? Remember, check for other chiral centers, right? Are there any chiral centers? So Shidza said diastereomers. Does anyone agree? Disagree? Okay. No one wants to answer. Well, let's look at this. This is probably the little thing that confused some people, right? Is this is Br and Br, right? So at this carbon, right, we have Br, Br, and then we have a methyl group, and we have this propyl group, right? Is that a chiral center? Even though the things are drawn on a wedge and a dash? No, right? There are no other chiral centers, right? So these CH2 groups, if you did a replacement test, you'll only get a pair of enantiomers, right? And they're enantiotopic, which means they're chemically equivalent. So here, right, between this one here, we get another signal, right? And then this CH2 group, which I'm now going to draw in pink, right? Is that equivalent to the other CH2 group? Just look at location. Right? No, it's 2 carbons away from the one with the bromine. It's next to a methyl. The other one is 1 carbon away from that, and it has a ethyl group, right? So this is also a distinct signal, right? So you have 1, 2, 3, and 4 total signals, right? So just because this question kind of wanted to trick you a little, right? That the bromines were drawn on wedge and dashes, but you just have to understand it's not another chiral center. And if there's no other chiral centers, like I said, all CH2 groups, right, they'll be enantiotopic, right? And in this case, you just check location to see if each signal is the same. So the pink and orange signal for the CH2, they're different because of location, right? So 4 signals here, right? We do that, right? Remember, so that when you do a replacement test, right, you only replace one hydrogen. So don't double replace basically. So don't keep one D here and then do another D, because then obviously you're going to get a pair of diastereomers, right? You only replace one hydrogen and then keep the rest of the structure the same. So that's one thing I want to clear about the replacement test. When you're doing it, you only do the replacement on one hydrogen, right? And then you could do another replacement test on another hydrogen, but you compare each structure separately, right? So if I did a replacement test here, it would be the same thing, right? This would create a chiral center at the pink carbon here, right? There's no other chiral centers. So these are enantiotopic, but they're chemically equivalent, right? Does that clear that up? Hopefully, Yep. All right. So 4 distinct signals, right? And then let's do J as well. Oh, actually, let me ask, how many signals did people get for J? maybe we could use the logic from the previous example and just now kind of see what's different here. And then, so Mohammed's at 5. Anyone else agree? Have more, have less? Damn, yo, everybody's shot today, huh? Okay, let's go over
I'm
it.
sorry, I joined like 15 minutes late, so I missed the explanation, but I'm catching up. That's why
No,
I would be answering. I usually would be like,
yeah, no,
jumping in to answer.
I'm just teasing y'all. It's all good, man. Don't worry. No one's required to. I'm not forcing anyone to like be like, yo, participate. Like, I just like messing with y'all. Okay, so I think we could all agree that first off, these methyl groups, right? Let's use different colors for all of these signals right now. So we have one here. We'll say this is blue, right? These are unique signals, right? They're different methyl groups, and we know all 3 H's there are homotopic in each of them, right? So we got 1 and 1 signal there. Right? That should be pretty clear. So let's use orange here, right? So what's not shown is this H, right? But there's no other H's here on the same carbon, right? So that H doesn't even matter. It's unique because you don't have to worry about comparing it to any other H here, right? So we get another signal from that hydrogen. So right now we're at 3, right? Now we look at the CH2 group. So let's pick, which color do we use? Pink. So let's use this one, pink, right? This carbon here. So we have H and H, right? If we did a replacement test here, right? We get D and H. And is there any other chiral centers here?
Yes.
Yes, right? So that means that both of these hydrogens, right, the original hydrogens here are diastereotopic. So do they produce 1 signal or 2 signals?
2.
2, right? So we get 2 here, right? And now let's mark this as green, right? This was H and H. Let's do a replacement test quickly on one of them, right? There's still that other chiral center, right? We're not really worried about the other CH2 group since we're not doing replacement on it, right? So we are forming a pair of diastereomers, right? So these are diastereotopic. So how many signals do we get from the green location?
2.
2 as well. So what's the total number of signals?
7.
7. Right? So if you are having a little trouble with these, try the rest of this problem, right? Because I want to move on to chemical shift. Right, so this is, sorry, someone's saying something?
Yes, sure. I remember for the number I, you said to only do it on the test on 1 at a time.
Yeah, so when you do the replacement test, right? Like if I were to do a replacement test, right, I wouldn't make a compound where I would do a double replacement, right? Essentially, I would never do this, right? Let's recreate this, right? I wouldn't do D here and D here, right? You can only replace one D here, and then now let's say you want to compare, then we can replace another D there, right? So that's what I mean by the replacement test is don't replace multiple things at once at the same time. When you do a replacement test, look at the structure you created and then compare it to other structures with that replacement test, right? So only do it once at a time, right?
Okay, got it. Thank you.
Yeah. So total of
Question, if you
7.
don't mind.
Yeah, no worries. It's a question.
Is it always the case if if the CH2 group, if there's like another diastereomer group, then it's automatically diastereotopic, but if there's no other diastereotopic groups, then it's automatically enantiotopic?
More or less, yeah. That's what I was kind of saying with the earlier with the CH2 groups, right? I don't know if you were here then, but essentially when you have CH2 groups, right? If you have any other chiral centers on the molecule, all the CH2 groups, the protons on each of them will all be diastereotopic, right? Because of that other chiral center, right? And then if you don't have any other chiral centers, they'll all be enantiotopic. So you'll basically going like if let's say you had 2 CH2 groups, if there was like in the first one, they produce 1 signal each, right? But then because in J we had another chiral center, right? They produced 2, so we got a total of we went from 2 signals to 4 signals from both those CH2 groups, right? and that increased. And then we have one more hydrogen here too, which made a total of 7.
Okay, got it.
Yeah.
Homotopic 1 signal, enantiotopic 1 signal, diastereotopic 2.
Yep.
Got it. Thank you.
Okay, so yeah, practice the rest of 15.5 if you're having issues with determining different numbers of signals. So 15.5, there's a bunch more in there. And then also in the second language textbook is problems 3.2. This is in the second language, so 2L. Well, make that look like 2 L's actually. Second semester, right? So if obviously I can't share those anymore, but if someone has those books, please share them with their classmates. So that's 3.2 to 3.10 in that book, right? Let me actually. I actually really like the second language book in terms of learning NMR and how to analyze and create spectra. It just goes down straight to what you need to know in terms of, problem solving, right? The main textbook chapters covered the full-on theory and everything behind NMR, which is important to know how it works, right? It's not just like, oh, this thing works, right? It's good to know why it works, right? And that has to do with magnetic fields and hitting it with a certain frequency of radiation, right? Like I said, for people who have BISCO, he's gonna teach you guys this properly as well. I'm sure Boson's already fully covered this, but those are good for signal questions, right? So signals, right? Use those for practice there. Okay, let's move on to kind of chemical shift, right? So for this, I kind of just I'm gonna go over what they have in the textbook because the reason I don't really like doing the questions is because it's a lot of the math stuff, and usually on both exams, like actually I don't know. It really just depends if you get a Spectra question. So the questions themselves, you can answer them. I just want to go over kind of how you can analyze whether things will be shifted more or the other. So let me actually share my screen from the second language book. Soda window. Nope. Okay. Give me a second here. Okay, so let me share my screen there. Okay, so hopefully everybody can see this here, right? Okay, so the chemical shift, right, or aka your benchmark values, right? It doesn't actually have a unit of measure, right? This has to do with kind of when you do the division, it really just comes down to concentration, really, right? So shift has to do with basically, so TMS is essentially what we call the 0 point, right? There are sometimes you'll see, things that are shifted in the negative direction. Those are usually in metallic compounds. But for the most part, all your guys are going to be dealing with is positive, like anything above 0, right? So our kind of internal standard we use is this thing right here, tetramethylsilane, right? And that was kind of determined to be at a shift, like at a benchmark value of 0. So everything in NMR is kind of based off that reference. So that way, when you publish something in a paper and, they tell you the chemical shift, you know what they're talking about in terms of a spectra, and you could reproduce it. You could run the reaction again, check the NMR, and if it matches up or very close to what the publication says, then you know you got your compound, right? This is why NMR is very important in terms of publishing work, because it helps chemists know that, you reproduce somebody's chemistry, right? So essentially there's things called shielding and deshielding, right? And basically things that are deshielded are downfield, right? So actually, sorry, let me share this on my, it's fine. It's okay. So you guys can see the mouse though, right?
Yeah.
Okay, so deshielded, right? When something is downfield, right? This is kind of where thinking about the ppm, makes it make a little bit more sense, right? So ppm is a way to measure concentration, right? So if you are increasing the chemical shift, you're increasing the concentration, right? So when we refer to protons as downfield or that they're de-shielded, right? Basically, right, it means that they can easily kind of, go into magnetic resonance, right? Because there's nothing preventing those protons from being accessed, right? And generally, you'll see these when they're connected to like aromatic rings or like, electron, like inductive atoms like oxygen or nitrogen, like heteroatoms or Cl, right? Because if you have something kind of, that has a high electronegativity, right? It's going to be pulling electron density away from protons, right? Because that thing's electron negative, right? It wants electron density. So if it pulls away electron density from protons, right, those protons can more easily, go under magnetic resonance, right? So that's why we call that de-shielding, right? Because we expect something to be that, can more easily be accessible to be in a higher ppm, right? Because it's going to be in a higher concentration since it can easily go and be detected, right? So that's why de-shielded things show up at, a higher chemical shift value, because just think of it in terms of kind of a logical sense that they're more accessible protons, right? Because there's less electron density around them. So they're close to something that's pulling it, whether that's an aromatic ring, heteroatom, alkenes, right? Things that are, want electron density, right? Or alkynes as well, right? So things that are de-shielded or downfield have a higher chemical shift, right? And the logic behind that is they have less electron density around them, aka they're de-shielded, right? And things that are upfield are more shielded, right? So they're closer to like alkyl groups, right? Or like, like CH2s or CH3s are far away from heteroatoms or electron withdrawing groups, right? And then that makes sense because now those protons, right? They're keeping their electron density, right? So it's harder for them to go under, magnetic resonance, go from a hydrogen to a proton and then, be able to be detective, right? So that's why they are in a lower chemical shift value or a lower concentration since they're less accessible, right? And that's what we mean by kind of shielding, right? Is they're more shielded, which makes them less accessible, which is why you see them at lower, shift values or concentrations, right? So that's why how I always remember chemical shift is think of it at just in the, the terms here, the ppm, it's a concentration thing, right? So things that are, more in like alkyl groups or like things that aren't close to like, oxygen or nitrogen or aromatic ring, right? Like, CH3 or CH2s, right? They're always going to be in a lower concentration since their protons are more shielded and less accessible. And then the opposite is true when they are closer to those kind of groups, right? Because now they're going to be less electron rich and aka de-shielded and more accessible. So that's how a good way to kind of always remember, like if you're trying to think about where a proton or like where like this peak corresponds to, right, is the lower value, the more farther away it's going to be from a electron withdrawing group, right? So here's the case here, right? This is kind of a nice little diagram here, or not diagram, like, examples, right? So we have our basic methane here where my mouse is currently hovering over, right? That's at 1 ppm, right? So now let's say we added iodine, right? And now if you'd notice at the 3 remaining hydrogens, right, there's a shift, right? It went from a low concentration, so it went from 1 to 2.2, right? So it got de-shielded, right? And the logic still makes sense. This is iodine. Iodine wants its electron density, right? Because it has a very large electron shell and it could accommodate that electron density, right? So you notice the shift here, right? It shifted 1.2. So if this was on the spectra, right, just the regular methane here would be around that 1, and then we'd see iodomethane, its protons right over here, right? And that makes sense of the logic, right? Is that those hydrogens are now closer to something that's pulling away their electron density. So they got de-shielded or less electron rich, right? So they went downfield, as that's what we call is downfield when it's becoming a higher and higher ppm, right? Or a higher chemical shift, right? So that's I always refer back to that logic to kind of think about, So a lot of people have issues with chemical shift. They just try to blatantly memorize, right? But like if you just understand what's happening in terms of the concentration, it makes sense in terms of electron density, right? So same thing here, right? Now, if we compare like iodine versus bromine, which is more electronegative?
Bromine.
Bromine, right? So that makes sense that it got shifted more because now these hydrogens, right, they're even more deshielded. They have even less electron density. So they went from like 2.2 up here to like 2.7 here, right? Because they are now next to a group that can, or, atom that's, through induction and withdrawing its electron density more, making these more, positive and more accessible for magnetic resonance, right? So higher concentration. And you could kind of see this trend here, right? You see Cl, it goes up even more. And then fluorine, the most electronegative atom, that's a huge jump, right? So that trend kind of like you could differentiate between protons that are next to different heteroatoms, right? And then obviously the amount changes things too, right? So bottom, kind of in the bottom here, we have just the regular methane, right? And now we're just adding chlorines one by one, right? And now these remaining hydrogens, right? They're getting more and more deshielded because they got more chlorines next to them, which are inductively withdrawing electron density and making that remaining hydrogens more and more accessible, which makes sense in terms of concentration. If they're more accessible, they'd appear at a higher concentration, aka a higher shift value, right? So that's why I said the second language is my opinion. That's how when I first learned NMR, I learned it through this thing, and it's awesome. So here's the thing: is in terms of now location. This is why you could see why I didn't want to do problems, because you kind of had to add up math, right? And then there's tables in here that'll kind of tell you how to do the math. But let's look at this kind of example we have here, right? We have 1, 2, 3 carbons. So this is chloropropane, right? So now let's look at this alpha position here that it's marked alpha, right? Those are the closest to our heteroatom, chlorine, right? Which means they are the most deshielded and the most electron poor, right? So the most kind of partially positive hydrogens, right? Which means since they're deshielded, they're going to be at a higher ppm or more downfield. And now you see the further you get away from chlorine at this beta position here, right? It went from 3.3 to 1.6, right? And this is why I meant by locations give you different signals, right? Because, they're next to different groups, right? So now this went down to 1.6, which makes sense because it's farther away from a, an inductive atom or electron withdrawing group, right? Which means that it's harder to pull the electron density from these hydrogens, right? Which means that they're going to be more shielded since they're keeping their electron density. So they won't appear in a higher concentration, right? Since they're less accessible, aka more shielded, right? So these are now upfield, and as progressively, now this is the gamma position, right? So now we're 3 carbons away, or 2 carbons away, however you want to say it, from the chlorine, right? And we went even more upfield, or got even more shielded, because now this chlorine is going to have almost a minimal effect on taking the electron density from these 3 hydrogens at the gamma position, right? So that logic of, in terms of, concentrations, how I always remember chemical shifts, right? Is that the closer you are to something that is going to make you more of a proton, right? Or more partially positive, the more downfield you'll be. And then the further away you are, right? The more upfield you'll be, right? And that's why the ppm, in my opinion, is the best way to kind of think about chemical shift. Because a lot of times they'll just give you the number, right? But if you always remember the chemical shift is a measure of concentration, you can always just remember that logic of what's going to be something in a higher concentration means it had to be more accessible, right? And now if you see methylene groups, right? So a methyl group, right, is something that's like CH3, right? So this is 0.9, right? Methylene means it's connected to a carbon that's connected to 2 other carbons, right? So in terms of kind of like, how would I say it? There's more like bigger atoms there that can pull on this electron density. So it could really be it's connected to two other atoms, I should say, right? So a CH2 group, right, is slightly higher in shift than a methyl group, right? Because it's connected to something that could eventually, you know, kind of grab some of this electron density. And then when you have like a CH group, it's connected to three other different things, right? And that shift goes slightly up because these protons become a little bit more accessible since they're next to, you know, everything is more or less more electronegative than hydrogen, right? So even if it's another carbon or whatever it might be, the more groups you increase next to that carbon that has a hydrogen, right? That's slight differences in shift. It's very minimal, but that's how you can differentiate between methyls, CH2s, and CH groups, right? Because of the connections to that carbon, right? And then kind of the main one you kind of always need to know is when you have oxygen groups. So an alcohol or ether, right? They give about 2.5 shift, right? So that makes sense because you're next to oxygen, extremely electronegative, right? It's going to shift any protons next to it, right? And then esters are even more because you have the oxygen group, right? So the direct oxygen atom, and on top of that, a carbonyl group, right? So there's a lot of electron withdrawal going in an ester compared to like an alcohol or ether, right? Because those are just one oxygen atoms. Here you have an oxygen plus the carbonyl group, right? So you have even more of a higher shift when it's next to an ester. And then a pure carbonyl group is less than both of them because really it's the carbon here, right? This carbon at the end of the carbonyl is partially positive. So it's not the same as an oxygen being there, right? So that's why you only get like a +1 shift, right? So I was saying, if you always refer back to the ppm and understanding what shielding and deshielding means, you could always understand when things will be downfield, aka deshielded, or when things will be upfield, aka shielded, right? So these are just predict the signal problems. So I'm gonna stop the share because I want to get into multiplicity, right? But if you want to like do the mathematical kind of questions there, share my screen here. Right, I will just list out those questions in both the main textbook and the, give me a second, I gotta open up the main textbook here. Okay, so in the second language book, it is going to be questions. Okay, no, actually, let me write main textbook questions. So in terms of if you want to predict the chemical shifts, right, I would just say practice 15.8, and this is main textbook. Right, like I said, that's why I wanted to go over examples because it's like you're probably not going to have to do too much math. It's more of a quantitative assessment, right? But like if you want to do like the specific math behind it, these questions, allow you to do that. And then in the second language textbook, 3.13 to, sorry, it's 3.13 to 3.18. So second language, second semester, right? So those are just predicting shifts, right? But that's why I like going over those examples because it kind of covers all your baseline stuff. Oh yeah, and then on page 47, right? So this is a very nice table. Is page 47? There's two tables actually. I'm trying to find the other one. I guess it is that one only. I swear there was another one. But page 47 has a table. This is in your second language, second semester book, right? That table, and I think there's probably one in your main textbook too. It basically gives you the approximate chemical shift for protons next to certain functional groups. So like, methyl, methylene, methine, then you have allylic hydrogens, alkynyl hydrogens, aldehydes, aryls, vinylic, right? Actually, Let me just copy and paste that into the notes here. Just realized that would be better to do. One note. So this table right here, right? So it gives you a good approximate shift. So this is the one table I would say, I hate saying memorize, but a good, this is one of the few things. NMR is one of the few things you're just going to have to remember through a little bit of memorization, right? Is because especially like I run NMRs usually weekly. So, you kind of have to know where you expect certain types of protons to be. Right. So, yeah, let's get into, what's it called? Let's do multiplicity. Actually, I guess we could do integration. It's not really any questions here. Actually, okay, I found a good question, right? So are we good on kind of the chemical shift, right? Without doing kind of direct practice problems. Like you guys understand what influences the chemical shift, AKA location, right? That's why I said that the second language textbook, is the best way to learn the NMR stuff, right? You read all of that and do all the practice in there, and you should be pretty damn good with NMR questions, right? So okay, let's do integration, or basically area under your peaks, right? So let me copy and paste a program, right? In case you do get a spectra that isn't like just gives you straight up values, right? You have to make sure you set an integration, right? So here, that load up. Here we go. Right. So we did, first thing was equivalence. We did number of signals. We did location of the signals, which was the, ppm, the chemical shift. And now this is kind of how many protons are under a signal, right? So here is an example of an NMR spectra, right? And this has to do with something called integration, or the area under your curve, right? Is compound with the molecular formula, blah, blah, has given the following Proton Nmr Spectra, right? And basically wants you to determine the number of protons that are in each signal there, right? So here, right, is if there's two ways you'll get spectras. They'll either give you the actual area under the curves, right? Or they'll just give you the number of protons in those signals, right? So here, right, we are given area values. So basically the way you do this, right, is you're going to kind of divide it by the lowest area, right? So that way you could you're basically making all the areas under each signal relative to each other, right? So always find the lowest one. So in this case, the lowest one is, let's use a different color, right? Is 9.1. Right? So to kind of determine how many protons are in each signal, right? We divide everything by 9.1, right? And 9.1. So here we'll get 1, right? Here 19.1 divided by 9.1. We could it's probably 2 point something, right? But basically you could say it's approximately 2, right? Because that's the thing, is like when you obviously do this in real life, you're not going to get perfect values, but when you're within a margin of error, it's fine, right? So 19.1 divided by 9.1 is approximately 2, right? 18.6 divided by 9.1 is approximately how much?
2.
2. And then what about 45?
5.
5, right? So we can basically say, because now we have these basically all relative to each other, that this shift here, right? This peak, I should say, right? Represents 5 hydrogens, right? This peak here represents 2 hydrogens. This peak here represents 2 hydrogens, and this peak here represents one hydrogen, right? So the integration. So sometimes they'll just tell you 5, 2, 2, 1, right? Or sometimes they'll give you the integration and they expect you to know that you have to make it relative to each other, right? Hopefully you guys get lucky and just get told how many hydrogens, right? So this is what's called like area or integration, is basically how many, that peak, it represents how many protons at that position, right? Oh, 1 second. Let me put my thing on charge before this.
Is it always relative to the lowest integration values when we're trying to find the number of hydrogens?
Yeah. So if you're given like, you know, the full integration values, like in this example, right? It's always you always divide by the lowest, right? Because the lowest one you could represent as 1. So actually, let me do an example where you might get like a little thing different here. Give me a second. Let's put this thing on charge. There we go. So one thing to also check too is the total number of protons. Do they match up, right? So in here we have H10, right? This is a 1H spectra, right? So are these kind of like, in terms of describing the protons, are these accurate, or do we have to multiply it by any number? Do they add
Accurate.
up to, yeah, so they add up to 10, right? So let me see if I could get an example what I mean by where you might not have that case. So, okay, actually the next one is perfect. Okay, right, so let's go down here. So a compound with the molecular formula C7H14O has the following NMR spectra, right? Determine the number of protons giving rise to each signal, right? So the lowest value here is 10.8. So 10.8 is 1, and then 65.7 divided by 10.8, right? So we could say this is basically around 66 divided by 11. So how much is this then? 6, right? So we have 1 proton here and 6 protons here. Does that match our formula?
Oh, so it doesn't, so multiply by 2?
Yeah, right. So that's the thing is, in this case, we'd probably have some molecule that basically, you know, had symmetry, I would assume, right? Actually, you could kind of tell it will have symmetry. What kind of molecule is this? This is just 1 O here, most likely.
And what kind of
Actually,
molecule, like the functional group?
yeah, it would be an ether most. Actually, no, it would be an alcohol in this case, probably. Yeah. So either ether or alcohol, I can't really tell. Yeah, don't worry about that right now when we get to full spectras. But either way, we have to multiply by these by 2, right? So now we get 2 protons and 12, right? And that adds up to the total number of hydrogens. So these peaks, they don't represent 1 and 6. They represent 2H here, and this represents 12H, right? So that's why, like, in case you do a division, right, and it doesn't add up to the total number of protons, just multiply by a whole number, right? So like 2, 3, etc., right? And, you know, make sure you don't like mess up the count, right? Sometimes you'll have to do that multiplication, right? But I mean, this is just to teach you, just in case you get these questions where you're given like these integration values like this, right? Generally, I very few times see them give you, they'll usually just give you the direct number of protons for each signal, right? But it's just, you know, I just want to make sure you guys know how to do it in case, you know, you run into it and you're like, oh shit, I don't know what to do, right? You know, yeah, I don't want to have people run into that situation, right? And if we did, let's just do 3.23, right? And I'll let you guys tell me how many protons are under each signal, right? So we have 3 signals here, right? 18.2, 19.7, 7, 7, right? That we'll call this A, B, and C, right? Take a minute or two, and you can tell me signals A, B, and C, how many protons each of them represent. Okay. Anybody else want to share answers? Somebody sent me a, so everyone's okay. 2 in each of them. Perfect, right? So if we did a division here, right? 18, 18, 18, right? So it'd be 1. This is approximately 1 and approximately 1, right? We have total of 6 protons. So we can multiply by 2 here to match that up, right? Exactly. Right, so 2 H's. And the reason these are probably 19 is because they're very close to each other. So there's probably some overlapping integration. And that's why you expect these to be just a little higher than 18 there, right? So 2H and 2H, right? Okay, so if there is, let's see if there's any other integration stuff. So those are actually all 3 the integration questions in the second language, but here, I actually found some. So in the main textbook for more practice, it is 15.11 to 15.13, right? So that's the main textbook, right? Okay, now let's get into multiplicity, which is one thing I think people always have difficulty with, right? Actually, let's take like a 5-minute break here, so everyone can relax their minds a little bit, get some water or whatever. And then we'll return to this. And then once we do multiplicity, then we can just start basically determining signals and stuff. I mean, reading NMR spectra. Actually, let me pull out one of my old NMR spectras, and I can show you how it looks in real life. Okay, I'll give like some people a minute or so, but let me just start writing up the problem. As last week, I just started drinking a lot more water, and so like basically cut out all soda. Like you could feel the difference. Hydro homies. Okay, so 15.A. Yeah, so drink your water, people. Shit is I used to drink a lot of soda, and then last week I went to the movies. I went to see Venom. I'm actually going tomorrow to see Bond. But I went to see Venom and I had a large popcorn and soda. And then when I got home, I just felt like my chest and upper body just did not feel good. And I was just like, and I woke up and it was still kind of bad. I took an aspirin and it got better. But I was like, all right, I think it's, time to lower the sodium and cut out all soda. And yeah, so I've been feeling a lot better since, and I haven't really drank soda. So even last night I went to the preseason Nets game and had to pay $7 for a friggin' water bottle. I hate stadium prices. Oh, good lord. Yeah, Venom was good. I enjoyed it. It's not like it's not like crazy like any of the Marvel. It's a fun movie though. I enjoyed it. I mean, it had some cheesy parts, but the end credit scene is all I will say. That alone was worth it. That's gonna be very cool. Yeah, Bond I've been waiting for forever. I'm a huge James Bond fan and spy films in general. And Spectre was kind of a letdown, especially coming off of Casino Royale. And like everyone probably says Skyfall, and it is a great movie. But out of all the Daniel Craig films, Casino Royale is hands down my favorite because it just nails Bond, right? His character, right? Especially like from the original Fleming books. It's a fantastic movie. But Skyfall was brilliant too, cinematography wise. The song, obviously, everyone loves Adele's song there, and the story wise and everything, action sequences, But I guess Casino Royale is more of a character film, which is why I loved it, and they just nailed Bond so well in there. They kind of built the base. But I heard this last one is pretty good because this is Craig's last film, and then we don't know who the next Bond is, so it should be good. Yeah, I like Craig as Bond. I actually love Pierce Brosnan as well, but he's what I call the best Bond to have the worst movies, except GoldenEye, right? GoldenEye was great, but like the rest of his movies were just kind of, the plot was so garbage, but like he was such a good Bond though. Kind of sucks for him, but yeah. And I guess I grew up watching Brosnan first, but I guess I put still Sean Connery is the best because he's just awesome, and then probably I put Craig second. He was a damn good Bond. Okay. So anyways, let's get to this question. So multiplicity, right, is basically, right, so we saw some of these signals above here, right? And if you see they have kind of multiple peaks here, right? So that has to do what's called coupling, right? And basically, when you're in, magnetic resonance, right, protons can couple with each other, right? And we've got the integration, we've got chemical equivalence, we got the location, and then the last. This is why NMR is so powerful because the coupling, it determines the number of peaks in each signal, and it tells you basically what group these protons are next to, right? Or how many neighboring protons it has, right? So those who have already learned it, right? A quick kind of explanation is protons, they couple, right, with unequivalent protons, right? And then this is actually mathematically determined by something called like J values. Like there's books on NMR spectra that like go into super detail behind the math and everything behind this, right? So the J values kind of determine how many distinct peaks you have. Then you have something called complex coupling, right? Where it's basically like things can split into what's called like a doublet of doublets, or like a triplet of doublets, something like that. But I'm not going to really go too much into detail of that. It's more just that, when there's certain different unequivalent protons, they'll couple a certain way. But the main thing you need to know is that the number of peaks, aka the multiplicity, tells you how many protons are next to the, those protons, right? So anything under a certain peak is all chemically equivalent protons, right? That's what this 2H represents. Those two hydrogens have the same chemical equivalence, right? And then the peaks in here, right? So in this case, we have 1, 2, 3 peaks. This is what we call a triplet, right? And basically, the formula you use here is n plus 1 equals your multiplicity, right? So here, our multiplicity is 3 since it's a triplet, which means n equals 2, which means this, whatever this group is, the 2H, wherever these 2H's are, there are 2 unequivalent protons next to them, right? So now let's do an example together, kind of do this all individually, right? Is that basically like when you have carbon-carbon bonds, right? The only way you can couple carbons is if they're if they're like on the same carbon and if they're chemically unequivalent, right? So let's say if we put a Br here, right? H and H here would be unequivalent, so that would count as one neighbor, right? Or so if they're on the same carbon or they're at most one carbon away, right? And then complex coupling gets into when they're a little bit farther and they can still kind of couple with each other, or like if different partners are different, right? That's where you get like those doublet of doublets, quartet of triplets, etc., right? But any neighbor is an unequivalent proton. That's really what you need to know. So, it can either be on the same carbon. So if you have diastereotopic protons, or it can be at most one carbon away, right? So first of all, we have protons. Let me just move this bottom example here. So we have protons here, right? So all the protons here, are they homotopic, enantiotopic, or what? Let me make that H look a little better. Homotopic,
Homo?
right? Right? So they're all on a methyl group, right? We know these are all chemically equivalent to each other. So are they neighbors to each other? Will they couple with each other or no? They're one, right? So they wouldn't couple with each other. I mean, technically they do, but in terms of the multiplicity, you wouldn't consider these neighbors. We could basically call these all HA, right? So these would not like couple with each other, right? Because they're not neighbors, right? A neighbor is any unequivalent proton, right? And like I said, it could be on the same carbon or at most one carbon or one atom away, right? So in this A, it doesn't, they're all equivalent. There are no neighbors, no unequivalent neighbors, right? I mean, I'll keep saying that, unequivalent. So in terms of determining multiplicity, right? So n plus 1, we said the neighbors. So how many neighbors are here? Look at the carbon next to it, standing proton. So 0, right? So these don't count, right? The other 2HA, they don't count. So this is 0 plus 1, right? So that's a multiplicity of 1. And what kind of peak is that? For those who already know how to describe those. Singlet, right? So that's what we call a singlet. So if this was showing up on NMR, right? So we're going to write this as singlet, right? It would just be one peak like this. Actually, we had an example of that before. I think so. Did we? Yeah, right here. So you see that leftmost peak, right? The multiplicity is 1, right? So that means this one hydrogen, right? It's a shift 2 or whatever, right? That means we could kind of tell that the structure here, right, is probably, this is an H, and then there's probably either like, I don't know, carbons next to this, or yeah, this would make sense if this was all carbons, or whatever, heteroatoms, right? There's no neighboring protons, right? Or if it was actually, this wouldn't be aldehyde. It's way too low to be that, but that's kind of what my point is here, is that actually this is probably might be from a terbutyl group. I'm missing one carbon bond here, right? So there are no neighboring protons here. So it would be 0, and that would give you a singlet that looks like this. Okay, let's go back down to the question at hand, right? So here, let's look at these hydrogens, right? Homotopic, enantiotopic, diastereotopic. So we say diastereotopic. Are we sure? Is there any other chiral centers here? Yeah, there's no other chiral centers, right? If we did a replacement test, all we get is a pair of enantiomers, right? And what did I say earlier? Are enantiotopic protons chemically equivalent or chemically unequivalent? Equivalent, right? So do these have any neighbors? No, right? There's carbon here and there's the oxygen here. To each other, they're equivalent, right? So n+1, right? 0 + 1 here equals 1. So what is this here? What kind of peak do we expect? Another singlet, right? All right. Now here we have another CH2 group here, right? Homotopic and enantiotopic, diastereotopic. Enantiotopic again, so they are equivalent to each other. So this is kind of the way a boson does his questions, is that he'll ask you for distinct signals and multiplicity of each signal, right? So here we could say these are equivalent, so we'll just call these HC. Do they have any neighbors? How many neighbors? 3, right? So these, okay, let's use a different color here. These 3 here are chemically unequivalent to these 2 HCs, right? Which means if it has 3 neighbors, 3 + 1 is 4. What type of peak do we expect here? So maybe for those who haven't seen the names, let me actually put up the kind of names you have. A quartet, right? So I'm going to actually copy and paste this table here. Actually, I'll just put it underneath so we could use it for the next problem, right? So number of neighbors, right? When you have 0, it's a singlet. 1 is a doublet. 2 is a triplet. And then we had 3 neighbors. So here we get a quartet, right? So quartet, right? And then the last methyl group here, homotopic and enantiotopic, diastereotopic. Homotopic, okay, so we could kind of label all these as HD, right? And what's the multiplicity, or what kind of signal do we expect? So now that means I'm basically asking neighbors and the type of peak. So there's 2 neighbors, which means what kind of multiplicity do we get? Sure, it's doublet. Remember the formula, right? So it's a triplet, right? So here we have 2 neighbors, which were HC. 2 + 1 is 3. 3 is a triplet, right? So if you were asked like this, this is generally a question that boson asks, right? Is what's it called? Like he'll give you a structure and he says, give me the number of distinct signals and the multiplicity. So this is how I always liked answering it, because he does this in Orgolab as well. Is that I kind of write like HA on the side, right? And then basically each letter represents one different signal, right? And you write that it is a singlet, right? Then you can write HB, right? Is a singlet as well. And down, right? You'll write HC is a quartet, HD is a triplet. So if you see that kind of question, this is kind of how he expects the answers, right? So I just basically map out every proton and then everything that's equivalent, give it the same subletter, right? So like these are all HAs, this is all HB, this is all HC, this is all HD, right? And then you could on the side write the multiplicity for each of those different proton. Right? Let's do another one. So let's do like two practice at least of the multiplicity, so everyone's on the same page. Let's do B, right? So here we have carbonyl. So in a carbon that has 3 protons, right? it can only be, well, really, so CH3s are always homotopic. That's what I was kind of mentioning earlier, right? Is if it's a CH3 group, internally, they will all be equivalent to each other, always, right? They'll always be homotopic, right? But in general, any proton you could classify as either homotopic, enantiotopic, or diastereotopic. Right? Maybe after I post the recording and I was explaining this in the beginning, I'm not sure if you were there, right? You could rewatch it and understand. I was kind of, what I was meaning by that. But that's what we mean by homotopic, enantiotopic, or diastereotopic. Those are essentially three ways we could label them. Homotopic, enantiotopic, chemically equivalent. Diastereotopic, chemically unequivalent, right? So here we have, okay, so let's start with the left side, right? So if we were to label all of these, start with the red color here, H, H, H. How many signals? Multiplicity. So Rania says singlet, and it's one signal, right? So we can all are homotopic to each other, right? There are no other unequivalent neighbors, right? So we get a singlet there, right? Because 0 is the number of neighbors, right? Okay, let's go down here. Use blue, H and H. Number of signals and multiplicity. Singlet, right? And one signal and a singlet, right? So we could call these HB, right? Same thing, no neighbors. They're both equivalent. They're enantiotopic in this case, right? And this is a singlet. Okay. Let's use orange here, right? So that proton there. Number of signals, well, I mean, that's kind of obvious. There's only one proton there, so it's going to give one signal. What's the multiplicity, though? Let's zoom out to make sure you see that little chart there. So 6 plus 1. So it's a septet, right? So we could call this HC, right? And you'll say this is a septet. It has 6 neighbors, right? From each methyl group, right? So how about this methyl group here? Let's color this. How many signals and multiplicity? What's the multiplicity? It's a doublet, right? So it has one neighbor, which is HC, right? It's only one, you can only go up to 1 carbon away, right? So it's a doublet here. So we'll call this HD, right? This is a distinct signal as well. This is a doublet, right? What about this methyl group down here? It's we're running out of colors. We're only taking one neighbor because we only go up to 1 carbon away, right? So D's, they're all equivalent, right? And C is the only unequivalent neighbor next to D, right? How we did kind of C has 2 carbon bonds, right? It has 2 carbons with hydrogens next to it, right? So that's why we got a septet there. But here, this is all the way at the end, right? So you only go 1 carbon max, right? So don't go up to 2 carbons. So the green and pink, right? You wouldn't go that far, right? So what about the green? What's the multiplicity, first of all? I think that should be easy. It should be the same. It's a doublet, right? This is a doublet, right? Is this a distinct signal though? Like kind of the way I asked that question should kind of give it away. So why isn't it a distinct signal? Or if it isn't, which signal doesn't match? Same as HD. Exactly, right? So this, right? So this is what I said about symmetry, right? Sometimes in CH3 group, you can't distinguish between this CH3 group and this CH3 group, right? Because there's technically a line of symmetry here, right? Cutting through that way, right? So if we rotated this molecule, how it is rotating in space, you can't say, you can't tell me the difference between the pink methyl group and the green methyl group, right? So those entire methyl groups are chemically equivalent to each other. So they do not produce the same signal. They do not produce different signals. They produce the same exact signal. So if you actually saw this is very characteristic of these isopropyl groups, is you'll always see this as you'll see a septet. I'm just gonna try as a horrible septet, but then you'll see with an integration of 1, right? And then you'll see a doublet, right, with an integration of 6H, right? And it's a pattern recognition, which the book covers, right? Is those methyl groups are chemically equivalent to each other, right? You can't differentiate one methyl group from the other. So that's what I said in terms of sometimes you'll have molecules so actually a perfect example on this is HA, it's a methyl group, but it's not the same as the pink or green ones, right? It's in a completely different location. It's connected to different things, right? But here, if we look at kind of how we do the chiral center stuff in terms of, priorities, right? If you look at the carbons, both of these carbons are connected to another carbon, which is a CH, which is connected to that oxygen, right? So location wise, they are in the same kind of location, right? And if you did a rotation too, right, you would see, you can't say, no, this is the top methyl group, this is the bottom methyl group. You'll never be able to say that, right? Because then I could just rotate it the other way and be like, okay, tell me now, right? So in case you did miss that, I probably mentioned that earlier, right? Is that sometimes you'll have CH3 groups that are equivalent to each other. Generally, if I were to give you quick examples, is usually in the isopropyl groups and terbutyl groups, right? Right. So and even if you see like an isopropyl like this, right? Or even groups like this where you have the rest of the structure, right? Like basically if you have 2 methyls coming off the same carbon, right? So it's generally you can see that in isopropyl or like in this kind of carbon, this kind of system where you have 2 methyls, you can't differentiate between each methyl here. Same thing here and here, and then also terbutyl. All 3 methyls on a terbutyl are equivalent, right? So those are quick kind of things to remember in terms of if you ever see like a 6H or a 9H integration, right? And then you see, well, there's pattern recognition. So that's actually on page 6. It's figure 15.18. So figure 15.18, right? Actually, I can just copy and paste that here too, right? Is kind of patterns you'll see for certain groups always. It can help you save time on figuring out what the structure is, right? So this is both in the second language book and the thing too, pattern recognition, right? So whenever you see like a 2H, 3H this is a quartet and a triplet, that's usually an ethyl group, right? An isopropyl group is usually on 1H followed by a 6H, right? So a septet and a doublet, right? It's hard to kind of see here, but you see that it is a doublet there, right? Your spectras will be a little bit more clear. And if they're not clear, you could always ask your professor to confirm, right? And then a terbutyl is just a singlet, right? Because the carbon next to it has no protons, right? So it's a singlet of 9H. So these are kind of patterns you could kind of always remember and then, quickly determine things, right? That kind of covers it for multiplicity. In terms of practice problems, I would suggest the following from the main textbook for the rest of 15.15, and I guess you could do 16 for extra. So this is main textbook. There's probably stuff at the back of the chapter. So these are, I'm just kind of pointing out the in-chapter questions. I'm sure there's more practice problems at the end that you could find too. And then in the second language book, the multiplicity questions are 3. Oh, that's not a 3, that's a 2. That's not a 3 either. 3.25 to 3.30. So that's 2L second semester, right? So those are more multiplicity questions. Okay, so with that that kind of covers all the different things you'll see in the spectra. Now, if you're given a spectra, right, you will be able to kind of determine what compound it is, right? So the last thing, I should have actually mentioned this before everything, but I guess it works out mentioning it at the end. So does anyone remember, maybe if you've had me from Orgo 1 or whatever your teacher or thing might be, it's HDI, or sometimes it's called the DOU, hydrogen deficiency index, or the degrees of unsaturation. Has anyone heard of that before? Right, so there's like a quick little formula you could use for that. I believe it's 2C, I think it's plus N minus H minus X plus 2, all divided by 2 equals your HDI, right? So the number of carbons times 2 plus any nitrogens minus any hydrogens minus any halogens, right? So this is only halogens, right? So if you have any oxygens, it doesn't affect it at all, right? And then plus 2, all divided by 2 gives you what's called the HDI, right? And that kind of tells you like the degrees of unsaturation or how deficient you are in terms of hydrogens, right? And any degree of unsaturation is something like an alkene, right? That's 1 degree, or a ring counts as 1 degree, right? Then that's 1, right? So 2 degrees would be something like maybe if you had 2 alkenes in one thing, or a ring, right? Plus an alkene, or even a triple bond, right? Right, something like that. Because there's 2 pi bonds in there, right? So each is a degree of unsaturation, right? A ring counts as 1 degree, a pi bond counts as 1 degree, right? And you could basically keep adding, right? So if I gave you a molecule that looked like this, how many degrees of unsaturation does this have? Remember, it's pi bonds or rings. Each degree of unsaturation comes from either something like a ring in a structure or a pi bond, right? So if you add up every degree, you'll get the total degrees of unsaturation, right? So the example kind of gave you here as a pi bond here, a pi bond here, right? So you're close, right? We have the ring as well. So we have the ring and pi bond, and then we have 2 here. So we have 2 from there, 1, 1. So we have 5, right? Remember the ring as well, right? So if we did kind of a structure, right? So if we did something like, you can always kind of determine this. So let's say we had this structure here, right? This is, shoot, you know what? Let's do something everyone's seen here before, right? What was this again? It has should remember the name of this. It's 1,3-butadiene. Your favorite Diels-Alders diene, right? So if we were to do this molecular formula, it would be 1, 2, 3, 4 carbons, right? So C4, right? And 1, 2, 3, 4, 5, 6 hydrogens, right? So 6 hydrogens is H6, right? So now how we can count, so we could physically see there's 2 degrees of unsaturation here, right? But this is why the formula is important, right? So if we did the formula here, so 2 times 4, right? Minus 6 for hydrogens. We have no nitrogen, we have no halogens, right? Plus 2 divided by 2. So on the top you have 8 minus 6 is 2 plus 2, right, is so it's 4 on the top divided by 2 is 2. So we have 2 degrees of unsaturation, or HDI, right? Maybe I should write DOU here as well, right? And that makes sense here too. Now, if we look at the structure, we have 2 pi bonds, so 2 degrees of unsaturation. So why this is important for NMR is because when you're given a molecular formula and a spectra, right, you could immediately kind of determine how many pi bonds or rings, or like basically it'll give you insight into what the structure is before you even analyze the spectra. And that's why it's super important, because you could just take the molecular formula, figure out the degrees of unsaturation, and you could be like, okay, this might have a pi bond and a ring, or it might have a ring, or it might have multiple pi bonds, right? So like a carbonyl too, right? So if you have a molecular formula with oxygen or whatever, right? So let's say we had this. So this was 3 hydrogens here, 2 here, and 3 here. So we have how many total? 7. So 8, 7, and we have O, right? And we have 1, 2, 3, 4. So C4, 8, 7, O. So 4, sorry. So it's 2 times 4 minus 7, right? Did I count those wrong? No, I didn't. Okay, just making sure. 3, 3. Yeah, I did count those wrong. It should be 8. Thank you. I just saw your message there as well, right? So minus 8. I was just like, we're about to get a non-whole number, and y'all gonna be even more confused. So anyway, we have 2 times 4. That's 8. Minus 8 is 0. Plus 2, right? All divided by 2. So this is 2 divided by 2, right? Equals 1, right? And now we know that something, if you're given this molecular formula, it's a good chance there's probably a carbonyl, right? And then you could look at the spectra, right? And then you have a kind of already insight that, okay, this might be a carbonyl. So I know one part of the structure kind of looks like this. And then you could look at, you know, the different peaks, their multiplicity, their integrations, and kind of build the rest of the structure based off that. That's why the HDI or DOU is very, very useful for NMR problems, because it could already give you insight into how your structure looks like, right? So one thing I should just mention, right, is the benzene rings, right? Generally, if you get a DOU of like, was it 5 or 4 and 5 and higher, right? There most likely will be a benzene ring in that structure, right? Because here we have 1 from the ring, right? And then 1, 2, 3 from pi bond. So we have a total of 4 degrees of unsaturation here. So generally, if you took a molecular formula, right, and you know, there was like, I don't know, let's say it was like C6, blah, 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 right? And you saw there was like the total degrees of unsaturation were like 5 or 6. There might be good chance that 4 of those are coming from a benzene ring, right? So you already know there's a benzene ring, right? So okay, let's analyze some spectra then, right? So let's start with the yeah, what's up?
A quick question. On the previous example you did, can you scroll up a little bit?
Yeah.
Up. Oh, yes, this one. You said it was 5. I still don't get it because I still am counting 4.
Okay, so let's circle them with different colors. So we have 1 from a pi bond here, 1 from a pi bond here, right? 1 from each pi bond in a triple bond, right?
Oh, okay.
Yeah, so
I see now.
so the triple bond, that's what I was saying here, is a triple bond is 2 degrees of unsaturation, right?
Okay.
Yeah.
Thank you.
Yep, no worries. And then 1 from the ring, so 5 total. Okay, so let's analyze some NMR spectras here. So I'm gonna give we'll do 2 problems from like the textbooks, and then I just wanna show you like a real life NMR spectra so you see how it looks. And then for those whoever watching the recording, I don't know, a few weeks down the line or whenever you guys go NMR, right? This hopefully should be helping y'all. So anyways, let's start with one kind of easy problem. So okay, so here, propose a structure for a compound with molecular formula C5H10O, right? And there's our spectra below. And on top of that, and they kind of weren't too nice, and they gave us the integration values, right? So first thing, what did I say to do is get the degrees of unsaturation. So here's our formula, right? Let's do it on the side here. Let's use red because that contrasts better off that, right? So we have 2 times 5, right? Minus 10 plus 2 divided by 2. So what's that equal to? 1. So we have 1 degree of unsaturation, right? So I said, looking at what's in there, what kind of functional group do you think there might be in here based off their formula? So you have oxygen, you have carbons, and you have hydrogens. What's a group that has a double bond to oxygen? Ketone or a carbonyl, right? So this one by itself, we just call those anything carbonyls. So just to put it off on your side, kind of, there might be a chance there will be a carbonyl here. Maybe it's an alkene, right? We're going to determine this later, right? Maybe maybe it's an alkene, maybe it's a ring. Probably not a ring though, because it's C5, right? So little things you can kind of notice, right? Most likely it's a carbonyl at some point in the structure here, or maybe an alkene, right? Now we kind of have to look at the shifts to determine what it actually is here, right? So let's start looking at things. So first thing, what should we do in terms of integration? You want to convert it to what? Divide by lowest, right? You want to make it relative to the molecular formula there. So what the lowest here is 27, 27 here, 27 there, 27 there. So this is actually a great example here, 27, right? So here we're going to get a 1, obviously. Here we get approximately 1, right? So now if you do 40 divided by 27, what kind of number do you get there? Approximately. It's not actually going to be a whole number here. So let me actually put that in my calculator too. So 40.2 divided by, what do you say, 27? It's about 1.48 here, right? So we did that actual math and it's 1.48. And here it says 42, it's probably going to be 1.5-ish as well. So we could basically say these are both approximately 1.5. So sometimes you do get that half number, right? But if we count these all up, 1 plus 1 is 2, 1.5 plus 1.5 is 3. We have a total of 5 hydrogens. How many do we have here? 10, right? We have 10 in the molecular formula. So now if you multiply all of these by 2, you actually get whole numbers, right? So this is why sometimes when you get that 1.5 or 2.5 or something like that, or half, right? You might just have to multiply by 2. This is why the integration is all relative to each other, right? And it'll always describe the appropriate amount of protons, right? So if we multiply all of this by 2, we get 2 protons, we get 3 protons, we get 2, and we get 3. So basically, we have 2 H's here, we have 3 H's here, right? And we have, what is it? We say 2 H's here and 3 H's here as well, right? So let's look up in terms of multiplicity and all this, right? So the one, let's also label these signals A, B, C, and D. Let's start with D. What's the multiplicity on D? It's a triplet, right? So this is 1, 2, 3 peaks. It's a triplet, right? Which means these 3 hydrogens, right? I have to take this off. These 3 hydrogens are next to how many unequivalent neighbors? 2 neighbors, right? So this is where all those pieces of the puzzle, I'm going to write these as nay, right? Is it going to come together? What's the multiplicity here? So now this is kind of what you'll see on actual. These are what are called satellite peaks. So you could kind of ignore them because they're not how would I say it? They're not really important in terms of the multiplicity, right? So sometimes you'll see satellite peaks. This might just be an impurity, right? But when the peak is really that small, actually, hold up. There's I'm looking at it. No, that's part of the spectra. Sorry, ignore what I said. This is probably just a satellite or an impurity. Okay, so what kind of multiplet is this? It has just count all of these, right? So ignore what I said. Those are not satellites. So what's the total there? So yeah, sextuplet, right? So it's 1, 2, 3, 4, 5, 6, right? So we have a sextuplet, right? Which means this 2H, how many unequivalent neighbors does it have? 5, right? So 5 neighbors, right? 3H here as a singlet. How many unequivalent neighbors? So 0 neighbors, right? And what about this one? This is a triplet. So this is 2 neighbors, right? Okay, so now we have a good idea of what's next to what. So let's start with do you see any patterns? If I went back to, if I zoomed all the way out, right? If we went to that patterns thing here, right? Or you could turn to this in your textbook while you look at this, while we're going over, right? Actually, I got an idea. Just copy and put it next to it. Copy, it's this button. Is there any patterns we see here? Kind of the ethyl one, right? But it's a slight difference, right? So we have a 2H, 3H. So we have the triplet. So that's most likely going to be coming from a methyl group, right? So that basically it's telling us there are 3 hydrogens with 2 neighbors, right? So we could say at one part of the structure, right, is essentially this is a methyl group, right? And it's next to a carbon that has 2 hydrogens on it, right? But what's the kind of difference between here? So this is a quartet. Damn, that's white. So this is a quartet normally, but we have a sextet. What does that mean that's next to that 2H group? Would it be a CH2 group, a CH3 group, a CH group? So if this has 5 neighbors, 3 neighbors are coming from a methyl, right? That means there's 2 other neighbors left, right? Which means we could basically already pick out one part of the structure is that it's a propyl group that looks like this, right? So whatever the rest of the structure is, right? We have, whoa, that's too many carbons. So it should be, so this is our methyl. So this would be D, this is signal D, this is signal C, right? And then C we know is next to, we're gonna have to determine one of these other signals, right? Actually tell me what signal would be the carbon, the coming off those hydrogens on the carbon next to C. If you look at the rest of the spectra, right? We have a singlet that has 0 neighbors, and we have a 2H that has 2 neighbors. So between A and B, that's kind of left. Which one would probably be next to that? A, right? And that makes now all sense, right? That D is a methyl group, a methyl group that has 2 neighbors, which is coming off C. C is a sextuplet, right? That has 5 total neighbors. So 3 are coming from D, 2 are coming from A, right? So this is why, but I mean, the more practice you'll do, the better you'll get at this, because I always treated it as a puzzle game, right? It's all putting the different pieces of the puzzle together and then getting the final answer, right? Or your completed puzzle, right? So now we basically figured out one part of the structure, right? Now we could also look at shift, right? So if you notice, right, the signal that we determined to be A is shifted to 2.4. Okay, I could go over it. So basically how we determined one part of the structure there, Shidza, is that we know we have a signal coming from something that has 3 hydrogens and one that's coming from 2 hydrogens. So normally that could just be an ethyl group that looks like this, right? So forget any other carbons it's attached to, right? This is going to be 3 H's, which we call D, right? That matches up the integration, and then it has 2 neighbors, right? HC, right? So that's a triplet because of its 2 neighbors, and it has 3 hydrogens at that signal location, right? So that's, are you good with how to get this D and C, right? So now C, right? Remember the total multiplicity of it was a sextuplet, which means that n plus 1 equals 6, which means it has 5 neighbors, right? So 3 of the neighbors we've already accounted for. Those are D. That means it's next to a carbon that probably has, or not probably, has to have 2 other hydrogens. So 1, 2, 3, 4, 5. And the only other signal that has 2 hydrogens is signal A. So these have to be from signal A, right? And now all the multiplicities and the integrations line up, right? So that hopefully, does that clear it up a little? How we basically got that part of the structure. Okay, now we could start looking at shift. So like, that's the thing, shift I usually try to look at last, because if you could determine other parts of the structure first, then the shift will confirm everything, right? So now this starts kind of making sense. Is we have, this is around 0.9, we'll say. This is about 1.6, right? The other 2H group is, right? So we have 2 HA and HC, right? They're both technically CH2 groups, but notice the difference. This is 1.6 versus 2.4, right? And what did we say? We have a degree of unsaturation that's either an alkene or a carbonyl, right? At this point, we've accounted for how many hydrogens? We've accounted for 7 hydrogens and 3 carbons. So what are we left with? We're left with 2 carbons and an oxygen. So if this is shifted all the way to 2.4, what kind of functional group would it most likely be next to? And this is coming from the degrees of unsaturation. What can shift hydrogens almost 1, basically? So if I went back to that little, let me get the picture of the signal shift. So notice HA and HC that we've determined here. C was at 1.6 and this is at 2.4. It's almost an approximate 0.8 to 1 shift. What kind of groove is A probably next to then? And it would make sense that it doesn't have any other neighbors at that point, right? So here and now we could basically add the carbonyl group. So that accounts for our 1 degree of unsaturation. And now it makes the rest of this once again make sense, right? Is A only has 2 neighbors, right? Because the carbon next to it has no hydrogens, right? So now we've gotten more of the structure, right? And the shift matches up too. D is the farthest away from that carbonyl group. So it's going to be the most upfield and most shielded. C is a little bit closer, right? Which is why it's 1.6. And then A is the closest, which is the most downfield or the most highly shifted, right? And then now the multiplicity of A also makes sense because the only protons it couples with are C here, right? and then the carbon next to it has no other neighbors, which accounts for its triplet. And now we only have one signal left, and if we've gotten 4 carbons, we've gotten all 7 hydrogens, there's 3 H's left, right? This is kind of another characteristic signal, right? It's shifted at approximately 2.1, right? And it's a methyl group that's usually around 1. So what is that group? It's coming off of what? If I gave you positions to like kind of attach this remaining group, say here or here, right? Where would we attach the remaining 3 H's and the 1 carbon left? Would it be at the carbonyl? Would it be at A? Would it be C? Or would it be D? The other side of the carbonyl, which accounts for why it's a singlet, right? And now we've gotten the whole structure, right? So this is a singlet, right? At approximately 2.1. We know generally methyl groups want to be around 0.9 to 1 in that range. So this is already downfield, right? So that, and it's a singlet, which means it's next to no neighbors, which means it's on the other side of the carbonyl. So generally when you see singlets, right, at this is another pattern that you could kind of tell is that's generally, and if you have the rest of the structure, right, that this functional group, this kind of acetyl group, right, is going to be a singlet of 3H at approximately the 2 range, right, which is what we see here. So this is a pattern they don't really mention, but it's one you could kind of remember, right? And now everything matches up basically, right? So this is B, right? So B was a singlet, no neighbors, it's shifted, makes sense, it's next to a carbonyl group. A is more shifted than C and D, right? Because it's closer to the carbonyl group, and then C and D, right? 2 H's and 3 H's, and boom, that's how you get your structure. So you used every little thing to come together and basically, fill out the different pieces of the puzzle, right? Okay, so second, just wanted to yeah, this is NMR is the one thing I will say, practice more than anything. So we'll do another problem, and then I'll just show you a real life signal, and we'll end on that. And so that way you guys have more practice from your that you could do from your thing. So okay, let's do one more. Let's do the next one actually, 3.47. Actually, wait, do we do 3. Oh no, actually, let's do 3.46. I'll give you guys, because you got, the thing is right now you don't remember like where, oh, whoops, that's the wrong thing. Actually delete that. And then I want to paste the problem, right? So let me actually also put one of the images from above that we had functional groups. Right, so this, like, there's certain stuff you're gonna have to remember, right? So this is what I'm putting on the side here, right? Okay, so propose a structure for the compound with the molecular formula C9H12 that is consistent with the following proton NMR, right? So first thing, what do we do? What do we check for before you even look at the spectra or anything? Degrees of unsaturation, right? So 9 times 2 minus 12 plus 2 divided by 2. So 9 times 2 is 18, plus 2 is 20, minus 12 is 8, right? Divided by 2 is 4. Okay, we have 4 degrees of unsaturation, right? And now this is where you see the kind of table I put on the, let me try to zoom in a little more. The table I have on the left, right-hand side there. This is kind of where, in terms of degrees of unsaturation, what did we say? What kind of group usually gives you that many degrees of unsaturation just by itself? A benzyl group, right? Or a benzene ring, right? So that we could fit a benzene ring in here, right? We have enough carbons to do that, right? We have 9 carbons here. So there's 6 of them could be coming off of benzene, right? And this is where knowing the general shift, like of where you expect certain protons, right? So here we have the arrow protons, right? Which are generally around the 7 range, so 6.5 to 8, right? You will find, this is why this table, you're going to have to kind of remember benchmark values for certain groups, right? I mean, I've done this enough where I kind of have a good idea, but like the other question, I just broke stuff down without remembering this table, right? Just doing it purely on everything else we learned. But this table, knowing these certain values will help a lot because they'll give you an idea at what those protons might be coming from. So that means aryl hydrogens are in this area. Do we see anything in that range on the spectra here? We label these A, B, and C. Is there anything in that ppm range? A, right? And we have 5 hydrogens on A. So right off the bat, without even working out the rest of the signal, and this is a multiplet too, right? Which is usually characteristic of a lot of things. I can already tell you that 6 hydrogens and 5 protons are going to be on a benzene ring. So we can start off by basically saying we know this structure based off that shift, this pattern recognition kind of, and the degrees of unsaturation, right? That we have something that looks like this. And there has to be 5 hydrogens, right? So that means basically this is a monosubstituted benzene ring, this whatever this molecule is, right? And what we kind of have else on it will be, what is it? You know, what other groups we have? Basically the 1 and 6 there in that case. So basically those 5 hydrogens we'll call signal A, right? So even though they are chemically unequivalent, that's the thing with aryl protons is that they're so close in their shift that they'll all just form together to form a gigantic, very like funky looking multiplet there, right? So that's why you have that gigantic multiplet, right? But basically they're not all chemically equivalent, but they're all like basically kind of on top of each other almost, right? So maybe the shift is different by 0.1 to 0.3, but we can essentially call these all coming from that signal, right? But I just want you all to understand that these two and these two are technically only chemically equivalent, these two and these two, and then this one, right? But the values, right, are so close that generally when you see aromatic protons or aryl protons, they'll just form this gigantic multiplet in their range because it's just a small difference, right? That's what I'm saying, they are chemically unequivalent, but because it's so close, it just jumbles up together when you take an NMR spectra, right? So, yeah, so we could say these were all, I'll leave those colors just to, make that point. But if it was asking for signals, yes. So if like this was a question where it gave you a structure, right, and said different signals, these would be distinct signals, right? This would be an orange signal, this would be the blue signal, this would be the red signal, right? But in terms of a spectra, they're so close together, they'll just show up as one gigantic multiplet, right? Okay. So we know basically right now there's a monosubstituted benzene ring. So at this point, what we're missing, right, is we have 6 carbons, right, and we have 5 hydrogens. So basically we're missing C3H7 at this point, right, for the rest of the structure, right? Is there any other patterns we see here, right, for this? Did we see that 6-1 pattern before? What kind of group was that? An isopropyl group, right? And this makes sense too, right? This is a multiplet. This is 1, 2, 3, 4, 5, 6, and 7. It's a septet with an integration of 1. and a doublet here, right? 1, 2, a doublet with the integration of 6, which makes sense, right? In terms of this is where your 1H, this would be B, and then this is where C's would be, right? They would all be the same signal because the methyl groups on an isopropyl are identical. And that's what I'm saying. Knowing the patterns, having a good idea of where certain things is, and like, we look how fast we did this question instead of looking at each signal, doing all the stuff, right? Just pattern recognition and the DOUs and all that stuff and the general areas of where protons are just, makes this so much more simpler. Is now basically what's our final molecule? It's a benzene ring. What group on it? With an isopropyl, exactly. So literally our final structure would just look like this, right? So sometimes if you get lucky and you could start identifying little things, these questions can be super easy actually. Like I said, it just takes a lot of this practice, right? And knowing the patterns and knowing where certain protons come up on the spectra, right? And this also makes sense in terms of their chemical shifts, right? Is the two methyl groups, right? They're farthest away from this aromatic ring. Remember, aromatic rings are kind of electron withdrawing, right? Because, they're pulling in electron density since they could, delocalize it well, kind of, right? So they're considered an electron withdrawing group in that regard, right? And then you could see that where that 1H is, right? So this would be signal B. It's more shifted because it's closer to this aromatic ring, right? So that would make sense that it's more shifted because that ring is pulling the electron density off of B more easily than C, right? So that's appearing at approximately 3.0. That's 1.0. So the shift values also match up as well, right? And here, this is a good thing too. Here is like you see this aromatic methyl, right? Like in this case, we have CH because there's 2 more carbons here, right? But it's the same kind of thing that applies. So you see like things that are essentially at the benzylic position. I don't know why they said aromatic benzyl. So really when you have things at the benzylic position, you could kind of consider them in that. So this benzylic position here, whether it's 3 H's, 2 H's, or in this case, 1H, right? They'll be around that 2.5 to 3 range, right? You could add that to your list of things as well too. So that one, you saw we did super fast. So in terms of textbook problems, right, what I would suggest for y'all to do to practice, there's a bunch at the end of I'm sure Bozon and Bisco have told you the recommended practice problems, but in chapter, it's 15.11 to 15.13. This is main textbook. Right, and then in the second language book, we did some of these, but it's basically 3.43 all the way to 3.48. Right, and then carbon 13, I don't really have too much time to cover it, but I mean, if you read the second language chapter, it's very simple. It all has to do with symmetry. Maybe next time before the next lesson or whatever, I'll do carbon 13. But anyways, the last thing I just want to show you is how a real life kind of NMR spectra looks like. So let's share that here. Okay, so this is the Bruker-Thompson program here, right? So these are actual NMR, spectra that I've, I guess processed or taken, really, right? So you see I have a bunch of different things I've tested. This labeling just has to do with in my lab notebook how what page number it is, right? So this compound specifically happens to be on page 28, right? And this is pure and isolated. This is so I'll show you actually what a crude NMR looks like, right? So this is when you run actual reactions and you just kind of briefly want to see if you got what you want. It looks nasty, right? It looks like that, right? And then you're gonna kind of have to try to identify certain peaks, right? But there's just a mixture of so much garbage. So this is a lot of how the NMR stuff that we get looks like. But when you actually have a pure and isolated compound, so after doing some chromatography, right, I managed to get a isolated compound, which is our final product here, right? This is our kind of main peaks of interest that I've already marked, right? And as you see here, right, can you tell me, like, because these are from that 7 to 8 range, what kind of group might I have in this compound? What shows up in that 7 and 8? So an arrow ring, right? How many protons do I have on there? There is, so the stuff at the bottom here is the integration. So I have 2, 2, and 6. So I have 10 total aromatic protons. So how many aromatic rings might I have? So generally you could have only a max of 5 or 6, right, on an aromatic ring. If there are 10 aromatic protons, there are 2 arrow rings, which is right. That's actually what I have, right? Here you can see highly shifted in like the 5, 4 range, right? There's 2 protons there, 1 proton there, 1 proton there. And if I was to draw up the structure, right, and you probably can refer to this in the recording and work through it backwards if you guys want to. And you could kind of work out all these locations, right? So I'll actually show you the structure, right? Which is this. So this was the compound I ended up synthesizing, right? So there's a aromatic ring here. Oops. And this was a product that came out of a result of cross-coupling, right? And you could see those 10 protons are coming from these 2 rings, right? And then we have, how many protons remaining then? So we had 10 there, and we had 4 more protons remaining. If I go back to that screen there, right? So there's basically hydrogens here, 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 and here, right? So there's 4 hydrogens. So we already counted for 10, right? Let me go back to share that screen, right? Right. Notice the bottom values are the integration values. How many do we have there? We have 2, 1, 1, right? That adds up to 4. So this is how in real life you could actually determine what you actually have there, right? This happens to be an isolated. This is why this one is so clean, is because this is pure and isolated, right? There are some other impurities, right? So this one right here at generally 1.54, that means there was a little bit of water in here, right? These are just other, grease or whatever. These are coming out of like stuff from the solvents, like stabilizers, etc. And then this gigantic peak here, right, that I've kind of like moving over, that's at 7.26. That's actually the solvent we use, which is deuterated chloroform, CdCl3, right? And it makes sense that that has the highest peak because that's the solvent it's in. And then that means there's also some water that was present in that chloroform, right? But the rest of the peaks all match up, right? So, I gave you the structures there. So for those who want to use this in the viewing the recording and want to work which protons are which, basically, you could try to tell me between these 2 protons, which ones do you expect? But these 2 right here, I'm going to tell you, you're probably not going to be able to get because it has to do with the face of the ring you're on, right? That's something you guys didn't really learn. But anyways, I just kind of want to show you how, like, a pure isolated one looks, something like a crude one. This is one I just ran recently, actually last week. Actually, no, that one's not crude. That's an isolated one I have as well. So this is another crude. Look how nasty this is, right? There's just so much garbage here, right? So but the thing is, that's the thing. Despite that, I was still able to find certain protons, right? To know, and then I basically figured out that I didn't have the product I expected because of the shifts, right? So that's the real life kind of example of what we do in our lab, and really what a lot of wet chemists kind of do in terms of determining like what you have, right? So that's like the biggest thing is proving that you made this, right? Because that's how you get published, right? So anyways, we'll end there. So I'm gonna stop the share here. So super tall, right? Like if you saw those super tall ones, right? That's usually the solvent, like the intensity, right? Because think about it, I only have a small sample of my compound, and then the rest of it is the solvent that's in it. Like, because it has to be in like a solution, right? So the solvent, you expect it to have the biggest peak because that's what's mostly in there, right? And then the other peaks show up because those, the solvent will only show, like the reason it's a deuterated solvent is that it shows up as one peak, right? That's your kind of benchmark, like to know that, okay, this is my solvent peak, everything else kind of matches up. So the solvent system that you use for NMR, right? Those peaks you always expect to be highest, right? I just happen to also have the water peak in there because clearly my chloroform or maybe even my sample was a little bit wet and it accumulated some, water in them. So that's why I had those two gigantic peaks. One was CdCl3, right? So that's deuterated chloroform, right? Chloroform is CHCl3. So CdCl3 is just deuterated. So that way it doesn't couple with the other protons, right? And then water is just H2O, right? And that shows up around 1.54. And that's why those two peaks are so huge, because there's probably that means there's probably actually a decent amount of water in either the chloroform or my sample, right? And then the chloroform was obviously the biggest because that's the solvent, right? For my sample, which is a solid, right? Okay. So yeah, so also, yeah, actually this is, you know what, let me bring that up again. I'll give you an example of this, right? Is the peak intensity, right? So let's see if I have one that shows this. So, oh, whoops. Yeah, so this is a perfect example. So this one that I'm currently showing, right? You see how intense these peaks are, right? This is a very highly concentrated sample. That means I put more of the substrate I'm analyzing, right? So whatever that oxetane ring I showed you guys, right? In that solvent, right? So that's why you see these peaks are even larger, right? In terms of their intensity, they're much higher, right? And now if you see the other one, which is the same thing I ran, right? But you see the peaks are much smaller here now, right? The reason is I put less of the sample in there, right? So I guess you could say, yeah, the concentration availability has to do with the intensity of the peaks as well. That's actually a very good thing you noticed there, right? But generally, like you don't want it to be too concentrated, right? So you don't get peaks confused and stuff, right? This is actually, good enough, right? To be able to, but the thing is, you don't want a too low of a concentration because then you see how these peaks are going down, right? Sorry, I'll actually shift to those. But if you notice that the peaks are going down, right? If you have too little of your sample, you won't be able to get an NMR spectra of it, right? So you need a decent amount of concentration. And usually in the Orgo lab class, if you take one, maybe or Orgo lab 2, they'll tell you like the right amount of solvent to put. And it's like basically the NMR tube. You basically put 3 fingers next to it and you want 3 fingers worth of your solvent in there. And then whatever your substrate is, right? So yeah, it's a good thing you noticed there actually in terms of the intensities, right? How concentration affects your spectra, right? So this was a highly concentrated sample, right? This was much less concentrated, right? It's the same exact thing. If I actually stack them, you'll see. So let me put this and I'll stack these spectra, right? You'll see, right? This is why NMR never lies. Your stuff, if you made something, it's always going to show it on the same NMR machine. Actually, for all NMR machines, it'll always show in the same location. You see these peaks are in the same position, same type of peaks, multiplicity, all this stuff, right? So NMR never lies, right? So even if so this is a question for the boson people who are going to watch this recording later. If you have like a 300 versus 600 or 900 megahertz NMRs, the frequency of your radiation, right, or really the resolution as we call it, right, has no effect on the chemical shift, right? So if you're asked a question where he'll tell you, the following molecule exhibits a chemical shift as 2.2 on a 300 megahertz NMR. What is the chemical shift at 600 megahertz, right? And what did I just say about chemical shift? It never changes. So if it was 2.2 at 300, well, what will it be at 600 or 900 or really anything? It'll still be 2.2. That's kind of the beauty of NMR, is that doesn't matter the type of machine and everything. Everything is made relative to each other, because that has to do with the strength of the magnetic field and the amount of RF, your frequency of your RF radiation, right? And that all kind of, it will always basically correspond to the same number, right? So it doesn't matter if you have 300 or 600, right? All that changes is how clear all your, peaks and everything is. That's why we say it's increasing resolution, because when you're running a 300 versus 600, the peaks will be a little bit more clear, and like you'll be able to distinguish them better as opposed to 300, right? But the shift will never change ever, right? So kind of one of the key concepts of NMR, and that's why it's so useful, is that when people publish a paper and they ran it on like 100 megahertz NMR or a 500 megahertz, the one we have at the CDI is 300. I know if I make that same thing, right, and put it pure isolated into the NMR, I will get those same exact shifts, the same exact multiplicities, and the same exact integrations, right? And that's how chemists around the world can, can basically know we have something, right? And that's why it had to be standardized this way, right? So anyone can replicate someone else's chemistry, right? It's everything has to be kind of collaborative and able for other people to understand. Otherwise, your shit's kind of useless, to be honest, right? So yeah. Anyways, have a good rest of your weekend. Hopefully those who view this recording later covers everything for NMR. Take care. Yep.